Thank you. Hello, everyone. Today, I'm going to talk about our new randomized greedy inference algorithm for dependency parsing. This is a joint work with Jaakkola, my advisor Regina Barzilay, and Tommi Jaakkola. The success of a parsing system mainly lies in two aspects. One is the exactness of inference, and the other is the richness of the scoring function. These are the key problems in a parsing system. So let's look at some examples on how well the existing algorithms solve these two problems. For instance, the MST algorithm can do the exact decoding, but it has to use a limited scoring function, such as one with only first-order features. On the other extreme, we have a re-ranking method, which can incorporate arbitrary features, but is highly approximated because its search space is limited by the top K list. Somewhere in the middle, we have many approximation methods, such as dual decomposition. It can search in full space with high-order features, and it also works very well in practice. It achieves new state-of-the-art parsing performance. So in our work, one of the goals is to understand why an approximation method can succeed in parsing. We know that high-order parsing is NP hard, so it should be difficult. But it turns out that parsing can be solved well by an approximation method. So we make the hypothesis that parsing is actually easy on average. This hypothesis follows the observation that many other NP-hard problems can also be solved by an approximation method because they are easy on average. So in our work, we theoretically and empirically analyze the average parsing complexity and demonstrate that our hypothesis is true. We also leverage the analysis and introduce an even simpler inference algorithm, which outperforms state-of-the-art systems. Specifically, our model combines the strengths of dual decomposition and re-ranking. It can incorporate arbitrary features, just like re-ranking, and it can also search in full space, just like dual decomposition. Next, I will introduce this simple algorithm and provide some analysis on it. Let's first look at the algorithm. The core idea is to climb towards the optimal tree in a few small greedy steps. Thus, we name our method as the randomized hill climbing algorithm. On high level, we repeat the hill climbing algorithm multiple times with random initialization. And finally, we pick the tree with the highest score. For the hill climbing algorithm, it includes 3 steps. It first randomly samples a dependency tree as the starting point. Then it greedily improves the tree by changing one edge at a time. It repeats the second step until reach a convergence. And that's it. Despite that, the algorithm is very simple. It works well in practice and outperforms previous systems. Next, I will show you an example to illustrate the hill climbing process, namely how to climb from one tree to the target. Consider the sentence, I ate an apple today. Suppose that we start from a tree like this, and we want to end up with this target. Next, I will show you the sequence of changes to climb from this initial tree to the target. And here we assume that we can always make the oracle changes. We will update in a bottom-up order, which means each word will be updated before its head. First, we check the word I, and we don't need to change its head because it's the same as the target. Next, we check the word N, and we move its head to the target's apple. Then we move the head of 8 to the root, and the head of today to 8. And finally, we change the head of apple to 8. And this completes the climbing process. A noticeable point in this example is that the tree structure is not violated during the update. In general, we can prove that if we update the dependencies in a bottom-up order, we can transform any tree to any other tree and maintain the valid tree structure at any intermediate point. This is why we update dependencies in a bottom-up order and why the greedy method has a chance to work. If we learn perfect parameters, we can always end up with the global optimum. Moreover, we only need to use as few as d steps, where d is the Hamming distance between two trees. In practice, we climb the tree based on the scoring function. When we pick the head, we always pick the one that doesn't violate the tree structure and increase the tree score most. Because we always operate on a valid tree structure, we don't have any constraints on the scoring function. Therefore, we can incorporate arbitrary features into the model, just like re-ranking. However, a common problem of a greedy method is that the score distribution is not perfect, so it can get stuck in a local optimal. And our solution to overcome the local optimal problem is also very simple. We only need to do the random restarts. And empirically, we only need to restart the hill climbing algorithm a few hundred times. Basically, we randomly generate the starting trees from some certain first-order distributions, such as uniform distribution. And then we run the hill climbing, and finally pick the tree with the best score, with the highest score. One big advantage of this random restart is that we can do it in parallel, because each run is cheap and is independent to others. Next, I will briefly introduce how we learn an accurate scoring function. We adopt the standard max margin framework with select variables. Specifically, we search the parameters which score the gold tree to be higher than any other tree with a non-trivial margin. Follow the common practice, we choose the Hamming distance between two trees as the margin. In order to solve the objective, we adopt passive-aggressive online learning framework. In this framework, finding the argmax is required for each sentence in every iteration. And we use the same randomized greedy algorithm to find the argmax. So far, I have talked about our randomized hill climbing algorithm. Next, I will talk about some analysis on it. We provide theoretical and empirical analysis for the first-order parsing. And we mainly provide some empirical analysis for the high order. Let's first look at the first-order theoretical part. The first part of the analysis is to quantify the complexity of the search space, because the quality of the approximation highly depends on the search space complexity. For instance, we could ask how many possible trees are in the search space. We noticed that for a sentence with 10 words, there are already more than 2 billion possible trees in the search space. This seems to be bad because the algorithm has to search in such a huge space. Fortunately, the number of local optimum is much lower than the number of possible trees. For a sentence with 10 words, then we can prove that the number of local optimum is no more than 512. This is good because the hill climbing algorithm can only get stuck in the local optimal, so we care more about the number of local optimal. If there are so many such local optimal, finding the global one would be still challenging. However, if there are only a few of them, it's very likely that the algorithm can hit the global one with random restarts. In fact, we can find a tight upper bound for the number of local optimal. And the sketch of the proof can be found in the paper. So for any first-order scoring function and a sentence of length n, the number of local optimal is at most 2 to the power of n minus 1, which is much lower than the number of possible trees. However, even though this bound looks good for the short sentences, it's still too much for the long sentences. Fortunately, this is only the worst-case upper bound. So what about the average case on the real data set? Before I talk about the answer to this question, let me first explain how we count the number of local optima with an example. Here's the sentence and the corresponding scores. The counting algorithm is a modification based on the Schuler-Edmonds algorithm, which finds the maximum spanning tree. So first, it selects the best heads of each word independently, as shown by the red arcs. If it directly forms a tree structure, then the number of local optima is 1. However, there's a cycle in the graph. So the next step is to contract the cycle and count the local optima recursively. The key point here is that any local optima exactly reassigns one edge in the cycle. So for a cycle of size 2, it will have 2 branches. The first one is to reassign the head of John, and the second one is to reassign the head of Saul. Each branch now have exactly 1 local optima, so the total number is 2. So next, we use this algorithm to count the number of local optima on the real data set. And here is the example on the English. For half of the sentences has no more than 21 local optima. And 70% has no more than 121, and 2,000 for 90%. Of course, there are still some sentences with millions and billions of local optima, but they are very rare. This suggests that the actual search space is much easier than the theoretical analysis. We further check if such easy search space leads to the successful decoding in our model. Specifically, we compare the result returned by our hill climbing algorithm against the optimal solution returned by the MST exact decoding. So we can see that our algorithm returns the optimal solution almost for sure. For the short sentences length up to 15, it finds the argmax for all of the sentences. And for the long sentences, it also finds 99.3%. It finds the argmax for 99.3% of the cases. So this means easy search space indeed leads to a successful decoding. So this completes our analysis on the first order parsing. Let's look at some analysis for the higher order scenario using dual decomposition technique. Dual decomposition can provide a certificate of optimality when it finds a global optimal, and we utilize this certificate to make the comparison. In order to make the comparison, we first train the model using our hill climbing algorithm, and then testing with either hill climbing or dual decomposition. For dual decomposition, we re-implement the second order model introduced by Ku, and achieved 94.5% certificate rate on English. First, we make the comparison given that dual decomposition finds the certificate. We can see that in this case, our hill climbing algorithm also returns the same solution for almost all the cases. Next, let's look at the statistics on the overall comparison. On 98.7% of the sentences, our algorithm returns the same solution as dual decomposition. On 1%, it returns a better solution, and only on 0.3%, it returns a worse solution than dual decomposition. This suggests that, at least for the second order model, our algorithm is as effective as dual decomposition, even slightly better. So now let's look at experiments and results. We evaluate our model and all the baselines on the standard kernel dependency dataset. This benchmark consists of 14 different languages, 13 from 2006 shared task, and English from 2008. We use first to third order features, which are typically used in previous graph-based parsing systems, such as MST and tuple parsers. Additionally, we use different types of global features, which are primarily used in re-ranking. During both training and testing, we applied an adaptive restarting strategy, which repeatedly runs the hill climbing algorithm until the best solution doesn't change for 300 consecutive restarts. We compare against 2 baselines. The first one is tuple parser, which uses dual decomposition with third-order features. The second one is our previous MC-MC sampling-based parser, which also uses global features. As the standard, we use unlabeled attachment score as the evaluation metric, excluding punctuations. First, we compare between tuple parser and our third-order model. In this comparison, we use a similar feature set to tuple parser, and we can see that the performance is very close to it. This means our algorithm is as effective as dual decomposition. Next, we compare between MC-MC sampling-based parser and our full model. Again, they use the same feature set, and their accuracies are very close to each other. This means our algorithm is also as effective as previous sampling method. We can also see that by utilizing global features, we achieve about 0.6% improvement. In the second experiment, we analyzed the impact of initialization distribution. In our model, we generate the initial tree using the first-order distribution, but however, we can also use the uniform distribution to generate the starting trees. Perhaps surprisingly, we observed that the performance is about the same, even using the uniform distribution. This means the climbing result is not very sensitive to the initialization distribution. We further analyzed the impact of random restart. This time, we only run one hill climbing process without random restart. We can see that the performance significantly drops by 3%. This means the random restart is essential in our algorithm. Next, let's look at our analysis on the convergence property. Here shows the example analysis on English. We first run the hill climbing algorithm with 3,000 restarts and use the highest score to approximate the global optimum. Then we plot the convergence curve as the function of the number of restarts. To facilitate the comparison, we also normalize the score by the approximated global optimum value. We can see that most of the sentences converge very quickly. Actually, for more than 98% of the sentences, it converges within the first 300 restarts. Next, let's look at the trade-off between the speeds and performance. The x-axis is the decoding speed from fast to slow, and we control the decoding speed by tuning the number of random restarts. The more number of restarts we do, the better performance we can achieve. And here is the example result on English. We can see that our model can achieve the high performance with an acceptable speed. For the third-order model, it's about 2 milliseconds per token, while for the full model, it's about 4 milliseconds per token. In conclusion, we analyzed the average case parsing complexity, and we introduced a simple randomized greedy algorithm by capitalizing the findings in our work. And this model outperforms state-of-the-art systems. The source code is available here. So that's all of the talk. Thank you.
Okay, do we have questions? Anyone?
Thank you. I was wondering if you, in addition to looking at the number of local optimas, have you looked at the quality of the different local optimas and if you have quantified how bad or good they are?
Yeah, that's a very good question. Actually, we want to do that. I mean, we want to look at the probability of the distribution of the local optimal, like what is the probability of hitting one global optimal, but we didn't come up with the good solution to that yet. So sorry for that. We are not sure about the answer. But in practice, yeah, I think most of the local optimal is actually very close to other and close to the optimal solution. So in practice, it's very likely to hit on local optimal, which is a good approximation to the global one.
So initially you were talking about an upper bound on the number of local optima. Does that mean in several cases from your random restarts, you're at a point where you can issue a certificate and stop doing any more random restarts and say, you know, we've already seen sufficient number of local optima? And in which case, how often does that happen?
So in practice, we don't run, so we didn't do that. I mean, we just use that adaptive restart strategy. Like we just stop based on the current best solution. We stop if the best solution doesn't change for many iterations, and we don't use the certificates by dual decomposition to...
I was thinking that you had a certificate because you had a bound on the number of local optima, so if you...
No.
But maybe that bound's very loose
yeah,
for anything other than
may,
very short sentences.
Yeah, we may drop into the same local optima multiple times, so we don't, we don't use that. And it's only for the first order, actually.
Yeah. Okay.
Yeah.
Other questions? Okay, if there are no more questions, then let's thank the speaker.